Hey everybody, welcome to section 3.4, the chain rule. The chain rule. So remember, we're in chapter 3. Our goal in chapter 3, our job in chapter 3, is to develop enough rules so that when we run across a function and we are asked to find the derivative of that function, we don't have to use limits. We never want to use limits again. So in this section, we're going to take a look at the chain rule, another rule that's going to help us never have to use limits. So in this section, we're going to find derivatives of composite functions using chain rule. We'll take a look at how we can modify that chain rule to make something called the general power rule. We'll do lots of simplifying of derivatives using algebra. We'll take a look at some transcendental functions and the chain rule and how it applies to those. We'll look at logarithmic functions, and we'll take a look at exponential functions that have bases other than the exponential term e. Wow, that's a lot. All right, so the chain rule. It is one of the most commonly, if not the most commonly used differentiation rule. It deals with composite functions. So it deals with functions of the form f of g of x. So back in your college algebra days, you would spend probably a couple of sections on composite functions. This is why. In order to differentiate or to take the derivative of composite functions, you have to use a rule called the chain rule. But in order to use the chain rule correctly, you have to be able to identify those composite functions. You have to be able to look at a function and say, that's composite. Here's the g of x, the inside piece, and here's the f of x, the outside piece. Okay? All right, so before we get there, though, let's take a look at the definition of the chain rule. The chain rule says that if y is equal to a function f of u, and it is a differentiable function of the variable u, and u is equal to g of x, and g of x is a differentiable function on x, then y can be thought of as f of g of x, and it's a differentiable function on x. And furthermore, dy dx, the derivative of y with respect to x, is going to be dy du multiplied by du dx. That's Leibniz notation. Or if you prefer, as most people do, function notation, the derivative of f of g of x is f prime of g multiplied by g prime. So we need to be able to do this correctly. We need to be able to look at this and say, I know which piece is g of x and I know which piece is f of x, because I have to take the derivative of plain old f, not f of g, plain old f, leave g of x alone, and then multiply that answer by the derivative of the inside, that is g prime. Okay? So basically what's going on here is the chain rule is talking about the rate of change of y and the rate of with respect to u, and the rate of change of u with respect to x. And says if y changes dy du times as fast as u, and u changes du dx times as fast as x, then the change of the entire thing is the rate of change of the first part times the rate of change of the second part as fast as x. Okay? Now, common notations will talk about outer function, inner function. So when I'm saying inner function and when I'm saying outer function, inner function is our g, also sometimes called u. Outer function is f. Okay, so just for some practice, identify the inner function, identify the outer function. Our first one here, we're given the function y equals the sine of 2x. Now I emphasize the word of there because very often, not all the time, not always, but very often when you read a composite function, the word of there is going to tell you which is the outside and which is the inside. So I'm going to say that again. The sine of 2x. Okay? So the inner function, the u, or the g of x here is 2x. The outer function, the f of u, is just the sine of u. Okay? We take a look at the second one. Y is equal to the square root of 3x squared minus x plus 1 of 3x squared minus x plus 1. So the inner function, the g of x, is going to be that 3x squared minus x plus 1. The outer function, the f of u, is just the square root of u. right, let's take a look at the next one. Y equals e raised to the cosine x. This is the example that breaks it as an always rule. I never said the word of. It's y equals e raised to the cosine x. But that raised to the, right, is what tells me about my inside, my outside function. My u, my inside function, my g of x if you prefer, is cosine x. My outside function, the f of u, is e to the u. Right? Y equals 1 divided by, right? Inside function, outside function, now this one's easier to see if you rewrite this. If you rewrite this, and what we would want to do to take a derivative, function raised to a power. The function is the inside, the power is the outside. Okay? Now, before we go ahead and start taking derivatives, let's take a look at one modification of this that we sometimes use, right? And it's this one right here. And it's relating to that last one we just took a look at up there. If, when you look at your expression that you're required to take a derivative of, or the function you're trying to differentiate, can be written as a u raised to an n, where n is a number. Remember that, right? So u raised to the n, then the derivative is n times u to the n minus 1 times u prime. So if your job was to take the derivative with respect to x of x plus 1 to the negative 1, do you see how this fits our definition? There's the u, there's the n, and so that's u raised to the nth power. Right? All right, so our job in this session is to learn how to use the chain rule. This is kind of like a special case of the chain rule, but it is part of the chain rule. And now guess what we're going to do? Example, 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 and then we'll move on to something new. Now, what you should take away from that is, if he's doing this many examples, this must be really, really important. All right, so let's get started. Our job is to take the derivative of every single one of these functions. So here I have a function, y is equal to the quantity 2x plus 1 raised to the third. So I'm looking at this and I'm seeing a composite function. Here's the inside piece, that's the g. There's the outside piece, that's the f. So my g of x is 2x plus 1, which means that g prime is 2. Okay? My f of u is u cubed. So then f prime of u is 3u squared. So chain rule says that then my dy dx is going to be n times u to the n minus 1 times u prime, or if you prefer, n times g of x to the n minus 1 times g prime of x. These are equivalent. It just depends on which one you want to use, which definition you're preferring to use. All right, so we got all the pieces and parts figured out. Now we just got to put it all together. So no matter how you're looking at this one, our dy dx is going to be 3 times the function u, but our u is our g of x, or our 2x plus 1, to the second power. That's coming from here. That's the f prime of u, or that's the n times g of x to the n minus 1. And then we need to multiply this by g prime, and g prime is just 2. And then we'll do a little bit of algebraic cleaning up, because it is unacceptable to leave it like that. We can't leave this 3 here and that 2 there and not multiply them together. They're both monomials. So we have 6 times 2x plus 1 squared. Now, if you're wondering whether or not you should multiply out that binomial, the square that 2x plus 1, the answer is no, don't multiply it out. Okay? All right, moving on to our second example. All right, so what I want to do is I want to start looking for those similarities. Does this one look like this one? Let's see. It looks like I've got a function raised to a power. So it looks a lot alike. Okay? So the u is x squared plus 1, and then the u prime, okay, or the g prime, however you want to look at that, is going to be just 2x. So then our dy dx, I'm still using this definition. Whoa. Let's undo that. I'm still using this definition over here, right? Our u prime is going to be 3 times x squared plus 1 squared times 2x. Okay? That's the n. Oops, not a capital N. That's the lowercase n. There's the u or the g of x. Right? There's the n minus 1. And then over here, that's the g prime. But of course, again, we can't leave it like that because that monomial and that monomial can't just sit there and not get combined. And so then we'll say that dy dx is equal to 6x times x squared plus 1 squared. All right, more. Here we go. Now we have a function whose name is f. This is where things get confusing and why some people like the u definition. Okay? But it looks like the same problem again. It's a function raised to a power. Right? So then a function raised to a power, the derivative function raised to a power, is going to be the power times the function. Oops, I'm writing way too big, so I'm going to start this one over. Okay? So then the derivative is going to be the power times the function raised to the power minus 1, and then multiply by the derivative function. Derivative 3x is 3. Derivative negative 2x squared is be negative 4x. Now that right there, as it said, is incorrect. Right? I need these right here. And the reason I need those right there is I need to multiply by that entire derivative. This whole thing is g prime. And if I don't have those parentheses there, it's not multiplying by the entire g prime. It's just multiplying by the term, the 3 there in front. Okay? And so then I will clean this up one step further because this monomial can easily be multiplied into that binomial. And I'm going to get 9 minus 12x times 3x minus 2x squared squared. And there's my derivative. Okay? All right. Is this one the same thing again? And if you answered no, stop for a moment. Remember, we don't have a rule for roots, so what do we have to do with this? We have to rewrite it like that. And if we're rewriting it like that, is this the same one as this one? Yep. Is it the same one as this one? Yep. Is it the same one as this one? Yep. Is it a function raised to a power? And anytime I see a function raised to a power, I know that the derivative of a function raised to a power is going to be the power times the function raised to the power minus 1, 2/3 minus 1 is 1, negative 1/3, multiplied by the derivative of the function. Okay? So I'm going to clean that up a little bit, and that's going to become, what is that going to become? 4/3, 2/3 times 2, x times x squared minus 1 to the negative 1/3. Now, if for whatever reason the direction said that negative exponents were no good, or that the answer should not contain negative exponents, I would just rewrite that as 4x over 3 times the cube root of x squared minus 1. Okay? So either of these, this one or that one, just depends on what the directions say. If the directions make no mention of negative exponents being a bad thing, go for it. Leave it as a negative exponent. If they say no negative exponents, put in the denominator. I guess there's a third option. I guess you could leave it like this. I mean, there's nothing mathematically incorrect about that. So I guess you could do that if it just said no negative exponents. And that does fix the negative exponent issue. Okay. Is this the same problem again? I don't know. Let's check and see. Because I'm looking at a fraction where there's only variables downstairs, so I'm thinking that maybe I should rewrite this as negative 7 times 2t minus 3 to the negative 2. Now, is it the same problem? Almost. Nothing else had a negative 7 out in front, or for that matter, nothing else had a numerical coefficient out in front. But that's okay because I got a rule for that. And the rule says if there's a number times your function, just pull the number out, take the derivative, multiply the number back in. So then it is just a function raised to a power. So then g prime of t is going to be that negative 7 times, let's see, the derivative of a function raised to a power is the power times the function to the power minus 1 multiplied by the derivative of the function. Right? So this negative 7 is that negative 7. This negative 2 is that exponent negative 2. And this 2 is from that derivative in there. Okay? And then, cleaning things up a little bit, I have 7 times negative 7 times negative 2 times 2. So that's 28. And so I get 28 over 2t minus 3 cubed. Okay, now, there was a student who complained in the last test that they got a problem wrong because the problem was written this way, and they wrote this as their answer. And they said, what does it matter? Well, it's this little tiny attention to detail thing right there that matters. What's the variable? The variable's t. If you write down x, is that the right variable? Now, I know what you're saying, but I did the calculus right. And yes, I will agree that you did do the calculus right. But it's that tiny little piece there, that attention to detail. And unfortunately, that little tiny piece right there is why buildings collapse and bridges fall down and planes fall apart in the sky. When someone forgets that one little bolt, that one little nut, because they were just like, oh, what does it matter? That's when the wing falls off. Okay? Or something tragic. The space shuttle that blew up years ago. It blew up because of an O-ring. An O-ring that went bad because someone didn't want to replace an O-ring. Right? So be careful. If the problem is delivered to you with the independent variable t, then your answer better be written in terms of the independent variable t. Okay? Hey, is this the same problem? You bet it is, because I don't have a rule for roots. So what am I going to do? I'm going to rewrite it. And then now it's just a function raised to a power. So then our dy dx is going to be the power times the function raised to the power minus 1 multiplied by the derivative of the function. Derivative of x squared plus x plus 1 is 2x plus 1. And you'll notice that I did not forget my parentheses. Okay, so don't forget those parentheses. And now I could take this. I could take this and distribute it into there, but I don't know that I like that. I could fix this and throw that downstairs if the rule said, or if the direction said something about no negative exponents, but I don't have any directions like that. The only thing I might do is I might do this, and this is how you'd usually see the answer represented. I don't know why. I've never seen a rule that says you have to do this, But I will tell you that it is very common for expressions, or functions in this case, or the derivative is a function, that when there are multiple terms which are being multiplied together, that if one has an exponent and the other doesn't, we usually put them with the non-exponent first and the exponent second. There's nothing mathematically wrong with it written in the orange line. It's just usually you'll see it written like the blue. Okay. All right. Is this the same problem again? And the answer you should say is no. This is suddenly different. Because if I rewrite this one, I'm going to have to rewrite this as x squared times the quantity 1 minus x squared to the 1/2. And so what is this now? Well, that multiplication right there makes this a product rule. But what do we have hiding inside of the product rule? So inside the product rule, we have a chain rule. So here's where things are going to start to get ugly. We are going to have everything we've done before now with chain rule. So we are going to have products where we have to use the product rule. But one or both of the multipliers might be a chain rule problem. We're going to have quotients where one or both of the numerator and denominator in that quotient, the dividend and the divisor, either of them could be a chain rule problem. Okay? So you could have a chain rule hiding in a quotient. You could have a chain rule hiding in a product. You could have two chains hiding in a product. You could have two chains hiding in a quotient. You could have a chain inside of a chain, nested chain rule problems. And so what we have to do is we have to take this step by step by step. So I'm going to erase this, and I'm going to go back and say, okay, so if this is a product rule, then we call this one U. We call this one V. We said if U is x squared, then U prime is 2x. If V is 1 minus x squared to the 1/2, then V prime, here's where the product rule comes in, is going to be 1/2 times 1 minus x squared to the negative 1/2 times a negative 2x, or if we clean that up, we have negative x times 1 minus x squared to the negative 1/2. That's my V prime. Okay? Now, since this is a product rule problem, I know that the product rule tells me that, what does the product rule tell me? Product rule tells me that f prime of x is going to be u prime v plus uv prime. And I use all this over here to build that. So u prime is going to be 2x times plain old v, 1 minus x squared to the 1/2, plus u, which is x squared, times v prime, which was negative x times 1 minus x squared to the negative 1/2. Okay, so let's see what we can do algebraically with this derivative to simplify it. Right? Now, in this derivative, I am seeing two terms. Here is the first term. Here is the second term. In those two terms, I'm seeing common factors. There's an x and an x, so I could factor that out. There is also the common factor 1 minus x squared and 1 minus x squared, so I should be able to factor that out. Right? So that's going to give me a derivative, f prime, of x times 1 minus x squared. Okay, now here comes the tricky part. What exponent do I use right here? Okay? Because my choices are 1/2 and negative 1/2. Okay? Now the rule for factoring says that when you factor a common term or common factor out of two terms, and both of them have exponents, that you are to factor out the smallest, the least exponent. So which of those numbers is smaller, 1/2 or negative 1/2? And since negative 1/2 is smaller, that's what I'm going to factor out. Right? All right. Now, when I take an x and a 1 minus x squared to the negative 1/2 out of the first term, what's left? Well, the 2 will be left, and I will have a 1 minus x squared to the 1. Now, if you're wondering where that came from, I factored out a negative 1/2. When you factor out, you subtract that exponent. The exponent was a positive 1/2. So what is 1/2 minus a negative 1/2? Well, minus a negative makes it addition. 1/2 plus 1/2 is 1. Right? Plus the second term. Well, I took out this x right here, and I took this whole thing out, but I still have this x squared and that negative, so that really should be minus x squared. Okay, I'm not done yet. I have x times 1 minus x squared to the negative 1/2 times 2 minus 3x squared. And there's my f prime. Now, if you're wondering what happened, well, what should we do with this? Given that this is an exponent of 1, it serves no purpose to leave it in there. And if it serves no purpose, there's no reason why I can't distribute. And 2 times 1 is 2. And 2 times negative x squared is negative 2x squared, plus another negative x squared gives me a total of negative 3x squareds. And there's my derivative. Now, if you're wondering why do all that work, why can't I just leave it as the pink? Right? One, because we're not that lazy. And 2, because in a couple of sections here, we're going to actually start doing things with derivatives. And when we start doing things with derivatives, they need to be as simplified as possible. Okay? All right, that's at 26 minutes for this video, and I'm nowhere near done with all of the examples, so I will do a whole bunch more in part 2.